Now I've just rewritten Kirchhoff's voltage law in the phasor format here. So we've got the phasor voltage at the input end of the transmission line is equal to the voltage drop across the distributed resistance plus the voltage drop across the distributed inductance, which is L prime delta Z j omega. And then finally, we've got the voltage at the output end of the transmission line. So what I want to do next is just rearrange, do a little bit of rearranging of this equation here. And what I'm going to do is just I'm going to collect these voltage terms and the current terms together. So if we were to do that, we would see that V of Z plus delta Z minus V of Z. So I've just moved this to the same side as V of Z plus delta Z is going to be equal to minus R prime delta Z I times the phasor current plus the total impedance of the reactive element times the phasor current as well. I can divide both of these by delta Z, and to do that I'll just do that right there. So the delta Z, since they occur in both terms, will cancel out here, and I've got it in the denominator here. If I were then to take the limit as delta Z goes to 0 of the entire equation here, what you would see is that limit as delta Z approaches 0 of V of Z plus delta Z minus V of Z divided by delta Z. That's just the fundamental derivative definition of a derivative. So I could rewrite this portion of it as the derivative of the phasor voltage. I don't have to use partials anymore since the phasors are only distance dependent. There's only one independent variable there now. On this side, there is no delta Z anymore. Remember, they were canceled out. So that just is equal to minus R prime plus j omega L prime times the phasor current. And sometimes this is rewritten as minus Z times the phasor current, where Z is just equal to R prime plus j omega L prime. Next, what I would like to do is apply KVL to the circuit, and real simply, the application of KVL is that the current into node A, I of Z comma T, has to be equal to the current out of node A, which is just the current through the conductance, the current through the capacitance, and the current flowing out of node A, I of Z plus delta Z comma T. So down here we're going to write a KVL, and that, as I just described, is going to be the current into the differential transmission line element is equal to the current through the conductance, which is I of G prime delta Z. Then we need to add the current through the capacitor, I of C prime delta Z. And then finally the current flowing out of the differential segment of transmission line, which was I of Z plus delta Z comma T. So that's in the time domain. Sorry, these should be lowercase because we're in the time domain. And what I want to do now is just convert these to I want to use Ohm's law and the definition of the voltage drop or the current through a capacitor to rewrite these. So that's I of Z comma T. What's the current through a conductance? Well, I equals V over R, which since GE is 1 over R, that converts to I equals V times G. So we just get, for this segment here, we get V of Z plus delta Z comma T times the total conductance, which is G prime delta Z. Now we need to calculate the voltage or the current through the capacitor, which is just going to be C prime delta Z times the partial derivative of V of Z plus delta Z comma T with respect to T. And this comes from I is equal to C dV dt. And then we just need to add on this last segment plus I of Z plus delta Z comma T. So that's the application of the Kirchhoff's current law. And what we want to do next is just convert that over to phasor form. So that's going to be I of Z is equal to V bar of Z plus delta Z times G prime plus delta Z. Next, we're going to use the same trick that we used for the inductor, in that the derivative of the phasor voltage is just going to be J omega times the phasor voltage. And then finally we have the phasor output current. So there we've got Kirchhoff's current law written in phasor form for the transmission line. And I'm going to do the same thing I did before, where I'm going to just rearrange some terms. That's going to be I of Z plus delta Z minus I of Z divided by delta Z is equal to minus V phasor of Z plus delta Z times G prime plus J omega C prime. I'm going to do the same thing I did before, where I take the limit as delta Z approaches 0. The left-hand side of this equation just becomes the derivative of the phasor current, di of Z dZ, and on this side, delta Z goes to 0, so I'm left with minus V of Z times G prime plus J omega C prime. And so sometimes this one is just written as minus Y V bar of Z. So the derivative of the phasor current at the input end is equal to minus Y times V bar of Z, where Y is G prime plus J omega C.